Hello. In this video, I'll begin my review of the AP Physics C E&M exam. In this video specifically, I'll be introducing the notion of electricity and magnetism, or E&M, and some of the key concepts needed to begin learning about electricity. Before we begin, we have to define E&M, or electricity and magnetism. So, E&M is a topic in physics which covers the electromagnetic force, which is something we'll talk about later in this course, and topics relating to electric phenomenon, which are phenomena in physics that have to do with protons and electrons, and magnetic phenomena, which occur when these protons and electrons are in motion, or when they're moving. Now, you may have heard of protons and electrons before in the context of atoms. So, to give a brief physical picture for what we'll be studying in this course, consider this very crude model of an atom. In the middle of an atom, you have what's called the nucleus, which is some collection of these red and white circles. The red circles are meant to represent protons, and the white circles are meant to represent neutrons, which are electrically neutral particles. How exactly the nucleus is held together is a topic for an entirely different video series, but for the context of this course, we can just consider the nucleus to be full of protons and neutrons. And orbiting this nucleus, or moving around it in a circle, roughly, is an electron. And an electron is a negatively charged particle. And just as a note, this model is certainly not to scale. So what we saw above is that charges, or electrical charges, are very important when studying E&M. So it would be useful to characterize such charges and perhaps give some numbers to them. So to start, an electric charge characterizes the protons, electrons, and neutrons within an atom. So a proton, which is also sometimes denoted by a plus sign, is a positively charged particle. And an electron is a negatively charged particle. For the most part, this positive and negative are mainly convention, and you could imagine a universe where we swap the positive and the negative. But in keeping with this convention, we'll be calling protons particles that have a positive charge, and electrons those which have a negative charge. And neutrons, which we saw sat inside of a nucleus of an atom, are electrically neutral particles. So they have neither a positive or a negative charge. And the charge of an electron, which here we call negative E, so that's what this negative E is. It's the charge of an electron. E here is called the fundamental charge. So this is a very important concept in electricity and magnetism. The fundamental charge is the charge of an electron, and one can think of the fundamental charge as just some unit which measures the electrical charge. Another unit, called coulombs, also denoted by C, can be related to the fundamental charge by this formula here. So we see that one fundamental charge, or 1e, is equal to 1.6 times 10 to the negative 19 coulombs. So we see that coulombs are much larger than a fundamental charge. And, I mean, from mechanics, one way of thinking about this is that the fundamental charge is like, let's say, a millimeter, whereas a coulomb is like a mile. A millimeter and a mile both measure distances, but of course, a millimeter is much, much smaller than a mile is. In the same way, coulombs often measure the electric charge of a macroscopic object, like a block of metal, or a person, a door, something like this. Whereas the fundamental charge, or E, measures the electrical charge of fundamental particles, like the electron. And for the contents of this course, all electrical charges that we will see are multiples of E. So you'll never have something like, an object has 50.5 E. That's not something that will happen. It has to be a whole number because it has to be a multiple of E. And going back to the protons, electrons, and neutrons, a proton has a charge of 1 E. An electron has a charge of negative 1 E. And since a neutron has no charge, or it's electrically neutral, it has a charge of 0 E. So we see that protons and electrons are the smallest amount of charge that we can get. There's an idea in electricity and magnetism which says that charge in the system is conserved. This idea is known as the conservation of charge, and its statement is concisely put in this orange box below. So simply put, it says the total charge or the net charge of a system cannot be created or destroyed. Now, we should probably elaborate on what this statement means. So, moving back for a minute, let's look at this first bullet point. So consider a block of matter, which is electrically neutral. What this means is if you have just a hunk of metal, if it's electrically neutral, if you zoomed into that piece of metal, you would see an equal number of protons and electrons. So you have these plus signs which indicate protons and these minus signs which indicate electrons. So if you added all of these charges together, so remember that a proton has a charge of 1 E, and then an electron has a charge of minus 1 E. So if you added all of these charges together, you would get something like 1 E minus 1 E plus 1 E minus 1 E plus dot dot dot. And if you added all of these together, assuming that the block of metal is electrically neutral, these would add to 0. So the total charge would be 0. And this is also seen in your life. If, for example, you've ever laid on, let's say, a wool blanket before, or taken off a coat or a jacket, what happens in these systems is that the blanket, let's say here in this picture, the blanket is electrically neutral, just like our block of metal was up here. So the blanket has an equal number of these orange plus signs and these blue minus signs. So that means that it has no net charge, or its charge is 0. And when you lay on the carpet and then move away from it, there's some friction which is created, and that friction causes the motion of electrons from your body to the blanket. So if you look on the right of this image, if you then walk away from this blanket and you touch, let's say, a metal doorknob, you get shocked by the doorknob. And the reason for this is that when there's friction between you and the blanket, some electrons from your body move to the blanket. So what happens is that you are left with all of these positive charges. So your body, which was electrically neutral before, has an excess amount of plus signs, and nature would prefer for you to be electrically neutral. So when you touch a metal doorknob, what happens is that the electrons from this doorknob, which move around very easily, prefer to move over to your body, and that the feeling that you have when those electrons move over is the feeling you have when you get shocked. So this is a very simple example of how net charge can't be created or destroyed. So when you're rubbing the blanket, it's not that you're creating electrical charge on the blanket or on yourself. What's really happening is that some electrons from your body are just moving from one place to another, which leaves your body in an excess positively charged state. So that when you touch a piece of metal, you get shocked as your body goes back to being electrically neutral. And finally, looking at a very common example in E&M, what you'll often have to solve for is the total charge, let's say on two spheres. So on the left side, we have two spheres, one of which is electrically neutral, which is the bottom one, and the top sphere is electrically charged. So let's say it has a charge, so charge is often written as Q. Let's say it has a net charge of 8, or I guess here we have minus signs, which means electrons, so the charge would actually be minus 8e. So we have a charge of minus 8e, and then we have another sphere, which is the same size, and it has a charge of 0e. So what would happen if we brought these two spheres together? Let's say they touched very quickly. So we take the spheres and we touch them together. So what would happen when these spheres touch together? Well, we saw in the previous example with a person in a blanket then touching a doorknob, if there's excess charge, that charge wants to move from one place to another. So for us, we have excess charge on the top sphere, and it wants to equalize between the two spheres. So in order to do this, we say, okay, there's initially 8 here, and it wants to equalize. So there's more on the top sphere than there is on the bottom sphere. So if there's an equal number between the top and the bottom sphere, that would mean that we have 4 electrons, or a charge of negative 4e on the top sphere, and then an equal charge of negative 4e on the bottom sphere, so that when you touch these spheres together and then you move them away from one another, you're left with a system of two spheres, both of which have now an equal charge, the top sphere having a charge of negative 4e and the bottom sphere also having a charge of negative 4e. And just to connect this back to what we were seeing before, remember that E is really just a unit. It's a unit of charge, and for macroscopic objects like people or pieces of metal, the unit of charge that you use is a coulomb. So if you remember earlier, we saw that 1e, so if you write this out, this charge is equal to negative 4 times e, and e is 1.6 times 10 to the negative 19 coulombs. Similarly, we have this on the bottom sphere. So the charge is negative 4 times 1.6 times 10 to the negative 19 coulombs. So all I'm doing is I'm rewriting the charge in terms of coulombs, because coulomb is more familiar charge in everyday life. So when we write this out, we multiply 4 by 1.6, and what we get is negative 6.4 times 10 to the negative 19 coulombs. And same on the bottom sphere. So the top and the bottom sphere both have charges of negative 4e, or written in terms of coulombs, they have a charge of negative 6.4 times 10 to the negative 19 coulombs. And with that, I'll end my very brief introduction to the AP Physics C E&M exam. Thank you.